So in this video, I'm going to be talking about congruence in newborn screening. And by congruence, I mean trying to achieve congruent results between two different newborn screening laboratories, and even between multiple instruments within the same newborn screening laboratory. I'm going to be talking about this first for the example of the amount of some biomarker in dried blood spots. And I'm going to be using the example of cytosine, which is an important second-tier marker for newborn screening of Krabbe disease. And then in the second part, I'm going to be talking about enzyme activities in the case of lysosomal enzymes, for example, in dried blood spots. And you'll see these are slightly different. And I'm going to be talking about mass spectrometry, tandem mass spec, and also fluorimetry, let's say digital microfluidics. Fluorimetry, since both platforms are now in use for measuring enzyme activity in dried blood spots. Cytosine, of course, can only be measured by liquid chromatography tandem mass spec. Now, let me start with mass spec. And you all know that in mass spectrometry and tandem mass spec, we measure things using multiple reaction monitoring, MRM. And we detect some signal in the ion detector. You inject the sample, and the signal rises, and then it falls back to baseline. So this is the detector response, and we integrate the area under this curve. And sometimes this is called ion counts, but it's a bit of a misnomer because this detector really doesn't count ions explicitly like a Geiger counter going click, click, click. No. When the ions pass through the detector, it creates some voltage, and this is some sort of voltage change. But we assume, and it's justified, that the area under this peak is proportional to the number of ions, okay? But this area is not exactly the number of ions. It's proportional to it. Okay, so I will call this the MRM signal. This area. Okay. All right. Now let's talk about how we might measure the concentration of cytosine in blood using a dried blood spot. So we're going to end up with concentration expressed as nanomoles of cytosine per liter of blood. All right, so let me just tell you the result, and then I'm going to prove it to you. But what you need is some sort of standard curve to play this game. And what you would like is some sort of curve that links the assay response. And I'll tell you more about this in a minute, what the assay response is in the mass spec, to the, I'm going to say the true, let's say, moles of cytosine in the sample. Now, why do I say true? It means we assume that we know the actual truthful moles of cytosine in the sample when we generate this standard curve. And how would we do that? Well, we might take a tube of blood, and to it we add known amounts of cycosine. And when I say known, I mean known truthfully. So at the end of the day, it means we have some stock solution of cycosine of some known true concentration. We add a certain volume of this to the sample, and that gives us the true moles added. Now, I'm going to talk to you about how do we know it's true, but let's assume it's true for the time being. So I generate this standard curve, I add true moles of cycosine to the blood, and I measure the assay response. And I get some sort of curve, maybe it looks like this. So this is 0 moles added, this is, 1 picomole, whatever. This is 2 picomoles, etc. I get some curve, and usually it's linear. I've got some data points. And you notice the line is linear, but it doesn't go through the 0 assay response at 0 moles of cycosine added. And, there's different reasons for this, this non-zero result. One reason, obviously, is that there could be endogenous cycosine in my original blood sample. And the other thing is there could be components of the blood other than cycosine that contribute to the assay response. So this is some sort of blank. And what you normally would do is you would subtract this non-zero value from all of the measured values, and you would end up constructing a line that goes through the origin by subtracting the blank. Right. Now, how do we use this curve to go forward with a new sample? It's pretty straightforward. So we have our curve. This is true moles cycosine assay response. It's been blank subtracted minus blank, and we have this curve. So then, on some new sample, we read some assay response, we go over to the curve, and we pull off the true moles cycosine. Okay. And this is a valid process. But, of course, it requires that our standard curve is generated using true moles of cycosine added to blood. Okay. Now, it doesn't really matter exactly what the assay response is and how it's generated. It's just enough to know that the assay response is proportional to the true moles of cycosine defined by the standard curve. Okay? And different labs might measure cycosine by different methods. They would have different assay responses. But as long as they have their own internal standard curve, they could play the game and determine the true moles of cycosine in a new sample using this standard curve. Now, I need to tell you very carefully, and this is very important, about how do we know that our stock solution of cycosine, the concentration is true. Is it really what it are? The moles of cycosine in the vial really what we think it is? So one way to do this is we can buy 1 milligram cycosine from some vendor. It's commercially available, and we could assume that there's 1 milligram in the vial, and then we can assume that it's pure, and then we could add 1 mil of methanol. And we know the molecular weight of cycosine, so we calculate the molarity of cycosine in the stock solution. And then if we add a known volume of that to the blood, we know how many moles of cycosine we're adding. And that would be true as long as our molarity is true. So there's two major problems with this in general. One is often the vial containing such a small amount of a lipid like cycosine, 1 milligram, this is often a nominal amount. an amount. The manufacturer doesn't guarantee it's exactly 1 milligram. They probably even say on their website that this is not accurate. It's a nominal amount. It's about 1 milligram. But an even bigger problem, you know, you could take this stuff out of the vial on a very accurate balance and weigh it, but that's not good enough because you have to assume in this process that it's pure by weight. Okay? And this is the tricky part. So if you weigh exactly 1 milligram of cycosine and you divide by the molecular weight to get the moles of cycosine, that only is true if every bit of the cycosine, the solid that you weighed out is cycosine. That is, that it's pure by weight. And you have to be careful with purity by weight. It's often sold not pure by weight. In fact, the vendor might even say that it's greater than 95% pure, and that was indeed the case for some vendors that sell cycosine. They stated that it was 95% pure. And that comes from some sort of chromatography. Maybe they did HPLC, where they look at the retention time and maybe the UV absorption of the material coming through the column. You know, and they get more or less a single peak. Maybe there's another little peak, and this peak and that little peak leads you to believe that it's 95 or greater than 95% pure. But, you know, of course, that's a very dangerous and inaccurate thing to say, because there very well could be impurities in the cycosine that do not absorb UV light and do not give a signal in this process. For example, maybe the cycosine is 50% by weight water, right? There's water everywhere, and you're certainly not going to see the water in this UV trace. Maybe there's heavy metals, maybe there's fingerprints, maybe there's residual silica gel. In fact, almost always these compounds analyzed in this way are essentially never pure by weight. And I wouldn't be surprised if the cycosine sold by these companies stated to be greater than 95% pure is something like 50% pure by weight. In fact, I can tell you that is the case because we measured the purity by weight using a technique that I'll talk to you about later on. So this is a serious problem. You should not assume it's pure by weight, even if the company says it's pure. So it's kind of very misleading. Okay, so how do you deal with this problem? So if the company says that it's a certified reference standard, and that they guarantee 1.1 milligrams of cycosine, not just solid but actual cycosine in the vial, this is something that you can use. And if they say certified reference standard and guaranteed, it is up to them to analyze what's in the vial such that the stated amount is the true amount of cycosine in the vial. And there's ways to do this, and I think the most powerful method is something called quantitative QNMR. And I'm going to tell you how QNMR works at the end of this video. It's kind of an appendix. You can listen to it if you're interested, but it's not mandatory. QNMR provides a way to actually count the number of molecules of cycosine that's in the vial. Okay? And it's one of the very few ways that you can do this. All right. So after a lot of trouble, and we had a lot of trouble getting congruence in cycosine values in blood between 4 reference labs that I'll talk about later, I finally convinced one company, Avanti Polar Lipids, to sell a certified reference standard for cycosine. And they now sell this, and they now quantify the cycosine in the vial by QNMR, and this is all good. It took some doing. It took some complaining. But Avanti, the very good company, they know how to do this, and they did it for the Krabbe field. Let's go back to this standard curve. And now let's assume you know the true moles of cycosine added to the blood because you use a certified reference standard. Here's your assay response minus the blank. Here's your standard curve. So all is good. Okay, now let's look a little bit more at this assay response and what it might mean. It could mean different things, but let's consider the following. Suppose you you measure the MRM signal for, I'm going to call it D0 cycosine because we're going to introduce this internal standard in a minute, which is deuterated. And suppose you add to your sample, your blood spot extract, some internal standard. And internal standards, the best kind, are always chemically identical to the biomarker of interest, but substituted with a heavy isotope. In this case, we can use cycosine that has 5 deuteriums, D5 cycosine. And you can buy that. Now, since this has a different mass, we can measure the MRM signal for the D0 and the MRM signal for the D5 because they have different masses. That's the whole point. And then we might take the ratio of the two, MRM D0 divided by MRM D5. And we could multiply this by the moles, well, let's say micromoles of D5 internal standard cycosine added to the sample. Okay. And since these are chemically identical, the ionization efficiency and the mass spec of D5 and D0 should be similar. So we might expect this to equal the micromoles of D0 in the sample. Okay? But that's not quite true. We have to worry about what's called the response ratio, or the response factor. What is the response ratio or response factor? So let's say we had a solution where we knew that the mole ratio of D0 to D5 was exactly 1.0. Mole ratio equals 1.0. And suppose we knew this to be true. So you might expect that the MRM for D0 to equal the MRM for D5, but often this is not the case. And yeah, these things ionize the same and they suffer the same ionization suppression, etc. But, you know, because of imperfections in the mass spec itself, because the quadrupoles, there might be some differences in tuning, there might be some biases. This ratio is often close to 1, but not exactly 1. So let's say it's 0.9. And how would you measure it? Well, you would simply put a solution that you know is mole ratio exactly 1, truthfully, into the mass spec, measure the MRM signals, divide them, and you get 0.9. All right. So if we want to know the micromoles of D0 into the blood spot, that's equal to the MRM for D0 divided by the MRM for D5, divided by the response ratio, equals 0.9 in this case, times the micromoles of D5, internal standard. Okay, so the 0.9 means that the mass spec is showing a little bit of bias. It's under measuring the D0 relative to the D5. So we have to up this ratio by dividing by 0.9. We have to multiply it by 1.11 essentially. Okay, and now this would be the micromoles of D0. Now, if you want this to be the true micromoles, then the amount of internal standard you added, the micromoles has to be known truthfully. All right, so to know the true micromoles of D0 in the sample, you have to measure the ratio of the MRM signals, you have to know the response factor, and you have to know truthfully how much internal standard you're adding. Okay. But actually, it's a little bit less complicated than that, because it's still true, even if the micromoles of internal standard you added to the sample is not really known truthfully. And even if you don't know the response factor, let's say you assume it's 1, or you can assume it's anything. Okay. You could still make a plot of, let's say, MRM for D0 divided by MRM for D5. You don't even use micromoles of internal standard in this assay response. In this case, you don't even use the response factor. You just simply use the ratio. We expect this ratio to be proportional to the amount of D0 in the sample. And if you generate a standard curve of this ratio versus the true moles cyclosine in the sample, and you get some background corrected curve that looks standard curve. Look, okay. You can use this curve to determine the true moles of cyclosine in your future sample just by taking the observed assay response that you get and reading it off the curve. Okay, so as long as you know the relationship between the assay response, no matter how you define it, as long as that assay response is proportional to the number of moles, and if you have the curve between assay response and true moles of cyclosine in the sample, you can play the game to get true moles of cyclosine in your next sample. Okay, and you don't need to know the response factor, and you don't need to be sure that you're adding a true amount of internal standard. In fact, you don't need to know these at all. All right, now to play this game, you need this standard curve. And if we go to another lab, they might get a different standard curve, even if they use the same instrument. So this is lab 1, and this is lab 2. Even if they use mass spec. And why would their slope be different? Well, their machine is different. In fact, their response ratio is probably different. So you inject a micromole of cyclosine into one machine, you get, or another machine, you get different. They might have different response ratios, and so the MRM ratios will be different. But it doesn't matter as long as you know the relationship of the assay response to the true moles of cyclosine in the solution for each machine in each lab. As long as you have the standard curve, you're good to go in that lab on that machine. Okay. So what do we need as a minimum to play this game? We need to know exactly the true moles of cyclosine in the sample. We don't need to know the response factor. We don't need to know how much internal standard we're actually adding. We just need to know the true micromoles or true moles of cyclosine present in the sample. Okay, so that's all you need to know to play this game as long as you have the standard curve. Okay. Now, let me say that again. Suppose you're in lab 1 and you have machine 1 and machine 2, and you take identical blood spot that has the same moles of cyclosine in it, and you put it into machine 1 and machine 2. You use identical solution of internal standard. There's no guarantee that the MRM to D0 to MRM to D5 will be the same on both machines, because the response factor could be different on the two machines. Remember, the response factor is determined by, how perfect the quadruples are working. It's kind of a calibration thing for the machine. And it very well could be different for the two machines. But you could still play the game if, for this machine, you have the standard curve of assay response to true moles of cyclosine in the sample. You have the standard curve. Okay, and for machine number 1, here's machine number 2, you have a different standard curve because the response factors are different, or maybe they're the same, you don't know. You can measure it. As long as you use this standard curve for machine 1 and this standard curve for machine 2, you're good. You can determine the true moles of cyclosine in the blood spots on either machine. Okay? Again, you don't need to know the response factor. All right. Now, what if we were to jump from one newborn screening lab to the other? Again, we could send the same sample, an identical sample, to both labs. And they might get different assay responses on their respective machines. But both labs would be able to play the game and get the true amount of cycosine in the identical blood spot if each lab had the appropriate standard curve for their assay response versus true micromoles. So, cycosine. So both labs have to know that they're adding a true amount of cycosine to their blood when they make their standard curve. And the only way they can do that is if they use a stock solution that's true in cycosine. And the only way they can do that, as I said before, is that they use commercial cycosine solid or stock solution, whatever they supply, that is certified to be true in the amount of moles in the vial. I think that's clear. And remember, not everything you buy, even if it's stated to be pure, is truthful in moles. It has to be guaranteed certified for the moles in the vial. Okay? Ideally determined by quantitative NMR, which I'll talk about later. All right. So that's pretty much all I want to say about determination of the absolute moles of cycosine in blood, or divided by the volume of blood, the concentration of cycosine in blood, except to say that this what I've been talking about is extremely important, and here's why. And this was described in a recent paper that I published in Clinical Chemistry, 2018, volume 64, page 1430 to 32. And I suggest you read this paper, but much of what I'm saying here is described in this paper. Okay. Now I want to go. Oh, before I do that, I want to say that what we're learning in newborn screening for Krabbe disease is we've developed a large data set to give us the following reference ranges that we're going forward with to improve the precision of newborn screening for Krabbe. And so the team of experts are getting together, and we're going to publish and to recommend some following reference ranges. For example, if greater than 10 nanomolar cycosine, we have never seen an early infantile Krabbe patient that did not have greater than 10 nanomolar cycosine. And we're going to say this is an emergency situation. We need to know the cycosine within a day or two after the GAL-C enzyme activity is known to be low in the first tier screen. And we're recommending that all newborn screening for Krabbe disease by GAL-C first tier be done by an immediate cycosine analysis when GAL-C is below the cutoff. And when cycosine is greater than 10 nanomolar, we feel that this is very likely early infantile Krabbe disease. The kid needs to be rushed for clinical exam, follow-up, and probably preparation for bone marrow transplant. This is an emergency situation. And so it's important, of course, that we do cycosine within a few days after we get the low GAL-C result. I think 2 weeks is too long. And so when you contract out your cycosine analysis, if you're not going to be doing it in the newborn screening lab, you need to make sure that the vendor, the CLIA lab that's going to be doing that can do it within a day or two. A week is too long. And we're going to say that cycosine around 2 to 10 nanomolar is high risk for late onset Krabbe disease, because we have something like 20 or 30 patients with late onset Krabbe disease that are known to have 2 to 10 nanomolar cycosine in their blood spots at birth. And again, the data is going to be published, but I just want to show you how important it is that we know these numbers very accurately. And we're going to say if your cycosine is less than 2 nanomolar, you're at very low risk to have Krabbe disease, and you should not even be informed that you might have Krabbe disease. We're going to set you free. Now, if New York were to do this, and they're going to do this going forward, they screen about, 250,000 babies per year. We think they'll have 0 to 1, maybe 2 early infantile Krabbe's per year, and I think 0 to 4 potential late onsets per year. So, now they typically get 50 or 60 or 70 samples per year that are Gal-C below the cutoff. Then they do genotyping, which is often confusing. If they were to do cycosine as their second tier test, they would have a very few number of patients per year that they have to be concerned with, and in fact report out as to families as potential Krabbe disease. And this, for example, is what Mayo is doing for the state of Kentucky, and the numbers are very small. So we really know how to screen for Krabbe disease now if you follow the cycosine story. But it also means that the labs that are doing cycosine have to get their numbers right. Okay, it's kind of like cholesterol. If your cholesterol is 180, you're okay. If it's 230, you're probably going to be put on statins. So 30% difference in absolute value of cholesterol in your blood is a big deal. And the same is true for cycosine. Okay, so what I've tried to do over the last 2 years is to sort of police the labs that are doing cycosine in the US, and not everybody can do this well, even if you're CLIA approved, because CLIA and CLSI do not really address these issues I've been talking about. They don't well address these issues in their guidelines. They don't really talk about certified reference standards for rare diseases, and for rare diseases, often there isn't certified reference standards because there's not a big market. For cholesterol, I'm sure there's very good certified reference standards, but not for cycosine until now. It took a lot of effort. So there are 4 qualified labs that have played along in this game, and I would say that is Mayo, Nationwide in Ohio, Columbus. PerkinElmer is now on board, and Orsini in New York Department of Health. He's going to be doing his own cycosine. And then my lab, but I'm not a CLIA lab. I'm just playing along to make sure we all agree on how to measure cycosine. And I have to say, we about a year and a half ago, I sent round-robin identical blood spots to these 5 labs, and we all got different answers, even as much as a factor of 2 off between labs. And this was traced down to the fact that we were using non-certified standards. And now that we've moved to certified standards, we all agree on the cycosine values to within about 20%. And we all use certified reference standard for cycosine from Avanti. And now we all agree. So what I don't want is another lab coming in, a rogue lab coming in and claiming they know how to measure cycosine when they're not playing by the same rules that we're using. I don't want them to be off in cycosine by a factor of 2. That would be a disaster. Okay? All right. So that's enough about absolute amounts of biomarkers in blood spots and congruence between labs and why this is important and how you have to do it using standard curves prepared in each lab on each machine. Things. Ideally, what we need are some QC cycosine dried blood spots, and my lab made a series of blood spots by taking whole blood, spiking with true amounts of cycosine using the certified reference standard. We made, I think, 0, 1, 2, 5, 15 nanomolar or something like that. And we sent these to the 4 CLIA labs that I mentioned. And so now we have a common set of QC standards. These guys can use them to prepare their standard curves, to check their standard curves. But the game only works if the standards are prepared from certified reference standards. Now, you can either use your own QNMR analysis to do this, or Avanti now sells this. So the CDC, for example, could make more of these materials as long as they don't buy 1 milligram vials, nominally 1 milligram of non-certified, as long as they buy the real deal, the certified guaranteed moles of cycosine in the vial, then you can play the game. And you see the importance of having a certified standard. Okay. So now I want to talk about congruence in measuring enzyme activities between different machines, between different assay platforms, and between different newborn screening labs. Okay, this is more difficult than cycosine. Okay, cycosine, we're interested in the amount of a biomarker. Now we're interested in the amount of enzyme activity in blood spots. So let's just think about the standard curve issue that we mentioned last time, where you measure the assay response minus the blank as a function of the true amount, I'll say, of enzyme in the sample. Let's say GAA for Pompe disease. Well, we have no way of measuring. What does it mean, true amount of enzyme in the sample? Well, true moles of enzyme. Well, that's fine, but we have no way of measuring that, right? This is not a small molecule that we can have a certified reference standard in a vial. All right, so we can't do that. So what does the CDC do? Well, they produce these quality control DBS, and they call them base, low, medium, and high. And let's look into, let's remember how these are made. So they take pooled blood from many donors, human donors, and they take some of that and they leukocyte depleted, and I don't think they can guarantee that every last leukocyte is removed from the blood. I'll come back to that. And then they do some sort of, I think, heat treatment or some sort of harsh treatment to sort of kill off most of the lysosomal enzymes. And this blood is now called the base pool. And so the B sample is 100% base pool, and they use that to make blood spots. The low is 5% blood plus 95% base pool. The medium is 50-50, and the high is 100% blood. Okay. So, all right, so let's plot. What do we expect? We expect, let's say, the assay response minus the blank in our enzyme assay. I'll come back to what this means. But here is our base pool. I'll put it here at 0% whole blood. And here's our high at 100% whole blood. Here's our medium at 50-50. And here's our, maybe it's here, our low at 5% whole blood. Okay, so you expect some linear relationship in assay response here. And here it is, nice and linear. You're pretty happy about that. And you notice it doesn't go through the origin again, 0 assay response. And why not? Well, there could be some assay response background that's not due to the enzyme of interest. And another problem is that there's no guarantee that the CDC got rid of all of the enzyme activity. I mean, most of the enzymes in leukocytes, they got rid of most of the leukocytes, but some of the lysosomal enzymes are in the plasma as well. We know that, and they heat treated. Maybe they didn't heat treat long enough. So the CDC never said that this has to go through 0-0. And in fact, it doesn't if you measure it carefully. But you still have a linear relationship that you expect, and you can verify linearity. That's a nice thing. I'll come back to this in a subsequent video, but I don't think it's particularly important to show linearity in the region of medium to high, because all of the action in newborn screening is somewhere down here at the cutoff, which is closer to the low than up here. I mean, nobody with 50% of normal activity has Krabbe disease, and I really don't care what the curve looks like out here. It really has no bearing. I would like it to be pretty much linear in the action region. Okay, so it's not clear to me that the CDC really needs the high sample, and in fact, in the next round, I'm in discussions with them to probably eliminate this and to create more samples in the region of the cutoff. And I'll come back to why that's important in a subsequent video. But another thing you can use these blood spots for is to have a common sample that can be shared between different instruments within the same lab or between different labs to try to achieve congruence. Okay, and that's important. Okay. All right. Now let's talk about standard curves and how are we going to measure enzyme activity. It's not the same as a small molecular weight biomarker like cyclosine, right? We have no way of knowing how many moles of GAA enzyme for Pompe disease, or GALC for Krabbe disease, or IDUA for MPS 1 is in the sample used to generate a standard curve. All right, so what do we do? All right. So what we do is we take the MRM for the non-deuterated product of the enzyme, which is generated enzymatically, and we divide by the MRM signal for the internal standard. Let's say it's D5 internal standard. I'll just call it internal standard. So these things are chemically identical but differentiated by deuterium replacing hydrogen. And we expect them to give similar MRM signals per mole. But remember, they don't exactly, because the mass spectra are not perfect, and we have this response ratio. So if you really want to know the true micromoles of product formed, well, that's equal to the MRM signal ratio divided by the P over IS response ratio, which needs to be known, times the micromoles of internal standard. And this should be true if we want this to be true. So for cyclosine, we did not need to know the response ratio, and we did not insist that this be true. Play the game, as long as we have a standard curve linking the assay response to the true moles of cyclosine in the sample. But we can't play this game with enzyme activities because we don't know the true moles of enzyme in the sample. Okay, so if we're going to achieve some degree of congruence between labs, now we have to make this true. So we do need to know the response ratio, and we do need to know the true micromoles of internal standard in the sample. So then, we take the true micromoles of product, we divide by the incubation time, product micromoles, incubation time in hours, volume of blood in liters, and we get the famous micromole per hour per liter number for our enzyme activity. And this is proportional to the amount of enzyme in the sample. Okay? And that's true. Now, we should know the true micromoles. There's a few other complications, like what if substrate is contaminated with some amount of product? So then some of the product signal that we see is due not to enzymatic generation from substrate, but from product that was introduced into the sample as a contaminant in the substrate. So, manufacturers should be sure that this is kept to a minimum, and newborn screening labs need to do some sort of blank For example, if you do a no incubation blank, so you don't allow the enzyme to incubate with the substrate to generate the product. If you introduce product from the beginning of time, because it's a contamination in the substrate, you should get some non-zero micromoles of product in the mass spec. And you could correct for that. All right. Now, all right. So this is all true if we're going to play the game of micromoles per hour per liter. But maybe we can try to simplify this a little bit, and let's consider the possibility of not expressing the enzyme activity as absolute micromoles per hour per liter, but percent of mean enzyme activity. All right. And for example, what New York does, I think, is they express gal-C not in terms of micromoles per hour per liter, but they get a assay response minus the blank for some newborn, some single newborn, and they divide by the mean assay response minus the blank, maybe the daily mean. Okay, and they assume that the daily mean, they do enough samples in one day that's representative of the population. And, that might not be true in a smaller state where they might be doing, 50, 60, 70 newborns per day. The mean activity might drift from day to day if they're not taking a representative slice of the population on all days. But that's less likely of a problem in New York because they're doing so many samples per day. But we worry about these things when we consider the daily mean. So maybe you want to use the weekly mean, and this is controversial, and I'm not sure I have an answer for you. But let's say everybody's using in their mean the same representative slice of the population, so that there's no variation in the representation of the population. So if you express percent of mean, let's say percent of daily mean, we don't really care about the response ratio because it cancels out. We don't really care about the non-truthfulness of the internal standard because it cancels out. So if one way to achieve congruence is not to worry about, we don't have to worry about the response ratio. We don't have to worry about the true micromoles of internal standard added. Just if everybody would to express their activity as percent of mean, we would expect to see some congruence. And I'm going to show you a very important exception that has to do with Pompe disease. I'm going to show you that very soon. That comes up between digital microfluidics and mass spec. It's a very special problem for Pompe disease. But in general, we expect to see congruence. Now, again, with the caveat that we are taking the same slice of the population in all states. Again, we don't need to know the response ratio. It cancels out. We don't need to know true micromoles. In fact, we don't even need to divide by the response ratio. We don't even have to multiply. We could just take the MRM ratio for the baby and divide by the mean MRM ratio across the population. And that would be exactly the same as anything else we would do more elaborate. It's good enough just to take this ratio because these guys would cancel out. Because this and this appear in the mean, and in the newborn they cancel out. All right. I think that's clear. Now, so let's say we don't want to buy into this plan of expressing the activity as percent of mean. We want to stick to micromoles per hour per liter. And now we want to achieve congruence between different labs. And this is very challenging. So if we're going to do this, we need to deal with the response ratio. We need to deal with true micromoles of internal standard. Okay, if we're going to take the MRM for D0 product divided by MRM for D5 internal standard, and convert it to the true micromoles per hour per liter. And said another way, suppose the response ratio in Texas is 1, and in Illinois it's 1.3. Then if I sent an identical newborn sample to the two different labs, they would get different micromoles per hour per liter if they ignored the response ratio. Okay? Because, let's say, in both labs they're generating the same true moles of product. It's the same baby, it's the same buffer, the same substrates, maybe even the same technician. But because the response ratios are different in the two labs, it's going to appear as different micromoles. So the way to get congruence is each lab has to know their response ratio so that they can divide by the response ratio in Texas or in Illinois, I think I said, and they would then correct. And they would have to know, of course, the true micromoles of internal standard added. Because, if Texas adds nominally 1 nanomole, but it's truly 2 nanomoles, and Illinois adds nominally 1 nanomole, but it's truly 1.5 nanomoles, then when they multiply by what they think is the true micromoles, which is not true, they're going to get different micromoles. Okay, so the only way to play this game, if we're going to insist on micromoles per hour per liter and congruence between the two labs, is that they both use true micromoles of internal standard, and they both measure their response ratio. Okay, so this is more challenging. And in fact, the problem, even within the same lab, if you have multiple mass specs, and they all use the same internal standard, let's say all true, but the response ratio here is 1, maybe here it's 1.5, here it's 0.7. The same sample measured across these 3 machines in the same lab using the same internal standards, it's going to give different MRM ratios, okay? And the only way to achieve congruence between these 3 machines is to know the response ratios for each machine and to divide each respective MRM ratios by the appropriate response ratio. Okay? So it's clear that we need to know the response ratios and use true micromoles of internal standard if we're going to achieve congruence between different mass spectrometers in the same lab or between different labs. Okay. Unless we go to percent of daily mean and we assume that the daily mean in each lab slices through the population in the same way. And you know what I mean by slicing through the population. Okay. So if we insist on micromoles per liter per hour congruence, we're going to have to measure the response ratios. In terms of the internal standard, it's my understanding that PerkinElmer provides in their kits or in their contract manufactured reagents, the internal standard stated in the vial is true. It's been measured by QNMR, so that part's okay as far as I understand. But we need to deal with the response ratios. So how do we do that? All right. So my lab made product internal standard mixtures, and this has to be done for each product and internal standard pair, so a different one from MPS1 and Pompeii and Niemann-Pick. And we use QNMR to measure. We don't really need to know the moles of P and moles of IS, we just need to know the mole ratio. Okay, this is done by NMR as well. And I'll tell you how QNMR works later on if you're interested. It's kind of an appendix. But okay, so I send you this vial, P over IS for Krabbe disease, and I tell you that it's 1.37 mole ratio. All right. So then, you measure the MRM. You shoot this into the mass spec for D0, the product, and the MRM signal for the D5 internal standard. And you get 1.20. And you should have gotten 1.37 because so apparently there's bias, your quadrupole or whatever your mass spec is under detecting the product. So the product to internal standard response ratio would be 1.20 over 1.37. That's the response ratio. And so then what you do is you take this number, you divide by that number, you multiply by the true micromoles of internal standard in the sample, and you get the true micromoles of product made by the enzyme. Okay, and then your micromoles per hour per liter. Presumably we know how long we incubated in hours. We know the temperature. We know how many liters of blood is in a 3 millimeter blood spot. So presumably the hours and the microliters are congruent between labs, and we should get congruent results across different labs in units of micromole per liter per hour per liter. Okay, but we need to use true internal standard, and we need to use the response ratio. And that's the reason I sent these vials. Now, we sent these to all labs doing newborn screening for Pompe and MPS 1 by mass spec. Most of the labs accepted them. It's my understanding that they're using them. Some labs, I think Wisconsin, decided they didn't want to use it. They don't need it. I think they should if they're going to report in micromoles per hour per liter and expect agreement with other labs in a congruent way. All right, so we supply these pro bono, and maybe the CDC should provide this. They'll have to have QNMR. The other option is GelbChem, this new company, LLC, can provide them. But, you know, I already sent enough for 10 years or something like that. So I really don't care who provides them as long as it's done by QNMR and it's well done. There's no money to be made here, so I'm not advertising that this should be done by GelbChem. Maybe we'd make a few $1,000s over 10 years. Okay, so if you want congruence and stick to micromoles per hour per liter, you're going to have these P over IS certified mole ratio standards, okay? Calculate your response ratios. And even, I should also say that if you have multiple machines in your lab, you need to know the response ratio across the different machines if you're going to get congruence. And maybe there's drift in these response ratios. You know, it's due to imperfections in the quadrupoles. Maybe it changes with time. So I'm suggesting that you measure these response ratios maybe once a week. And if it doesn't change over 6 months, maybe you go to a once-a-month plan. I think we need to get our feet wet, and I think I cannot get information out of major mass spec manufacturers about how much these response ratios differ from one, and what is the drift in these ratios as a function of time. So I think we're just going to have to explore this. So the bad news is that if we're going to do micromoles per hour per liter and expect congruence, we need to deal with these response ratios. The good news is that there's a relatively easy solution if we use QNMR certified P over IS standards. Okay, I think that's clear. Okay, I want to talk about congruence between mass spec and digital microfluidics fluorescence. So, okay, the first few things are pretty clear. So these two assays use chemically different substrates with different structures. So of course, the rate of enzyme conversion of substrate to product for these different substrates will be different. And also the buffers used are different. In digital microfluidics, they use individual optimized buffer for each enzyme, but in mass spec, we use kind of a single buffer for multiple enzymes, a compromise. So the enzymes tend to go a little bit faster in the digital microfluidics buffer than in the mass spec buffer because the buffer for digital microfluidics is closer to the pH optimum for the enzyme. Okay, so it's very clear that we cannot compare micromole per hour per liter with mass spec to, it's not equal to micromole per hour per liter with digital microfluidics fluorescence. Even if we use, identical sample applied to both machines. Just cannot do that. Now, let's think about the relationship between this activity, the enzyme, and the amount of enzyme. So you would expect that this is proportional to the amount of enzyme. So it's equal to alpha times moles of enzyme, moles of GAA for Pompe disease. Okay, and this is equal to beta times moles of GAA in the sample. And of course, alpha is not equal to beta because of the reasons I just said. So suppose there were zero enzyme in the blood spot, zero GAA. Of course, then the activity should be zero in both cases. All right. But actually, that's not quite true for Pompe disease, as you'll see. It turns out that in digital microfluidics, they're getting a larger contribution from an enzyme other than GAA. Okay, so even when GAA is zero, there's significant amount of activity measured due to the off-target enzyme acting on the same substrate as GAA. You'll see I can pretty much prove this from the published data. But let's ignore that for the moment. So if we plot micromoles per hour per liter for digital microfluidics versus the concentration of GAA starting at zero. We expect zero activity at zero, and then we get some line, presuming it's linear. In fact, it is. You can tell that by using the QC base, low, medium, and high blood spots. And for digital microfluidics and for mass spec, we expect some linear relationship. In fact, we get it. And they both go through 0, 0. But of course, the slopes of these two lines are different because alpha is not equal to beta. And in fact, the micromoles per hour per liter for any given amount of enzyme tends to be higher for digital microfluidics than mass spec, as I said, because digital microfluidics uses the optimum pH buffer. Actually, I'll show you in another video on assay imprecision and how it affects the performance of newborn screening assays. I'll show you that this slope really is not that important. It really has no value. The assay performance really doesn't depend on this slope to any appreciable extent, assuming the slope is not zero. Okay, I'll come back to that. That's not what really matters. The slope really doesn't matter that much. It's kind of surprising, but it really doesn't matter. All right. So, one way to deal with congruence between mass spec and digital microfluidics is, again, to give up on this micromolar per hour per liter thing, but to express everything as percent of mean activity. Okay? And then I think you see where this is going. Then in the case of digital microfluidics, you'd have alpha in the top, you'd have alpha in the bottom, it would cancel. And the same for mass spec. And so you should be able to compare with congruence if you had a sample newborn that was 10% of mean activity, population mean, it should be 10% in both platforms. Okay. Now, I want to talk about Pompe disease in particular. And let me show you the published data using digital microfluidics and fluorescence. Yeah, so this is the data published by Missouri. It's actually presented by Patrick Hopkins when he was director using digital microfluidics fluorescence. It was presented several times, including a newborn screening translational network webinar. So you see the blue bars are the micromoles per liter per hour for the Pompe enzyme measured on known patient samples. And in particular, look at the left part of the graph where you see looks like 8 infantile onset cases that have activities ranging from 2.5 to about 5.6 micromoles per liter per hour. And you can see the median activity in the green line at the top at 25. So some of these infantiles have as high as 21, 22% of residual GAA activity, it would seem. And then you can see the late onsets to the right, and they tend to be a little bit higher, but some are lower. And you can see how the cutoff was set to be just above the range of these values. And so again, you can see that the infantiles have quite high residual activity, a little bit over 20% in some cases, and this is just too high. So there must be an interference from the maltase glucoamylase enzyme, as I said before. So New York, I don't think has published the basis of their cutoff, but I have all the data from Joe Orsini in New York, and this table was taken from my publication in International Journal of Neonatal Screening, which I'll point out on the next slide. But so on the top, you have the values from Missouri that was taken from the bar graph, and then in New York, you can see the early onset values, and again, we can't compare the micromoles per hour per liter for mass spec in New York to that in Missouri with digital microfluidics, but I've converted to percent of mean, and you can see that the late onsets in New York, the bottom part of the table, are 15% of the GAA mean. Sorry, look at the right column. 4.8% of mean for the early onsets in New York, and 17.3% of the mean for the early onsets in Missouri. So 17.3% is the average value for those 8 patients. So clearly, even when we convert to percent of mean, there's no congruence between digital microfluidics and mass spec for Pompe disease. It's very clear. There's this shift, which I claim is due to interference from maltase glucoamylase being more severe for digital microfluidics fluorescence, given their assay, their buffer and substrate acarbose conditions. This is the publication that I wrote in International Journal of Neonatal Screening that has this data, and this story that I'm telling you about infantile Pompe is explained well in this paper. Okay, so we've established with high confidence that there's some contribution to the activity from some non-Pompe enzyme, and it's clear that this contribution is higher in digital microfluidics compared to mass spec. So really, micromoles per hour per liter for digital microfluidics is equal to alpha times the amount of GAA enzyme plus, let's call it gamma times the amount of off-target enzyme maltase glucoamylase. And for mass spec, micromoles per hour per liter for mass spec is equal to beta times the amount of Pompe enzyme plus, let's say, delta times the amount of MGA. And let's assume that delta is much smaller than gamma. In fact, I've shown you proof for that. Let's assume delta is essentially 0. So this term is 0, but this term is not 0. So it's clear that we cannot deal with the difference between alpha and beta simply by converting 2% of mean on each platform, because yeah, the alphas cancel out and the betas cancel out, but the gamma isn't. It's an additive term and it doesn't go away. So let me prove that to you. Suppose I give you a sample that has no GAA, so mass spec. According to this equation, if this is 0, the mass spec activity should be 0. But if this is 0 in digital microfluidics, the observed activity is not 0 because of this term, because MGA is not 0 and gamma is not 0. Okay, and that explains why Missouri reads something like 20% of mean activity for infantile Pompeii confirmed samples. New York is more like 5%. Okay, and this is in percent of mean, so the alpha beta problem should go away. Yet we don't get the same percent of mean. 20% for Missouri in digital microfluidics, 5% with New York in mass spec. And the reason is this additive term here. All right, so it's clear that we can't even get congruence between digital microfluidics and mass spec for Pompe disease, even if we convert our activities in micromoles per hour per liter to 2% of mean. We still will not get congruence. All right, so we have two solutions. One is we can subtract this 20% activity in digital microfluidics that we see due to the off-target enzyme. Or we could try to increase the concentration of acarbose in the digital microfluidics buffer until the off-target enzyme gets close to 0. This is a little tricky for two reasons. The first reason is that the acarbose is not 100% selective for MGA over GAA. So if you add too much acarbose, yeah, you can get the MGA contribution close to 0, but you're going to start inhibiting the GAA because the inhibitor is not 100% selective. This has been published by my lab. The other problem is you can't just use the same concentration of acarbose in the two buffers, because acarbose is a competitive inhibitor. So here's of MGA. So here's MGA, the enzyme, and it binds acarbose, and it forms an enzyme inhibitor complex with acarbose, which is dead, can't bind substrate. But acarbose and the substrate bind to the same active site on MGA, so substrate can bind to MGA, and this goes on to MGA plus product. But the substrate and the acarbose bind to the same site on MGA, so these bindings are mutually exclusive, and so acarbose binding to the active site, substrate binding to the active site competes. They compete with each other, and even if I have acarbose in the sample, I can overcome the inhibition, the conversion of some of the enzyme to the inhibited form. I could prevent this simply by jacking up the concentration of substrate. If I use enough substrate, all of the MGA is pushed over to the substrate complex. This concentration drops to 0, and in fact there's no inhibition. So one of the properties of these kinds of inhibitors, which are called competitive inhibitors, is that the percent inhibition by the acarbose can be brought to 0, no inhibition, if I use high enough substrate. I can bring all the enzyme to the enzyme substrate complex, overcome the inhibition. So said another way, even if I use identical acarbose concentrations in the digital microfluidics buffer and the mass spec buffer, even if I use the same concentration of acarbose, the percent inhibition of the MGA will be different because the substrate concentrations and their affinity for the MGA enzyme substrate concentrations are different. Okay, and so if the digital microfluidics has a higher substrate concentration than in mass spec, I would have to use a higher concentration of acarbose to get the same degree of inhibition. In fact, this seems to be what's going on, because if you look at the acarbose concentration that is used in the digital microfluidics buffer, it's pretty close to the concentration used in the mass spec buffer. They're not exactly the same. The mass spec uses a little bit more. But I think the real issue, the real problem is that in digital microfluidics, they use a much higher concentration of substrate than we're using in mass spec. And that overcomes a lot of the inhibition by acarbose. And this explains, I think, very clearly why even blood spots with 0 GAA give 20% apparent or activity by digital microfluidics. The activity is not due to GAA, it's 0 GAA, it's due to MGA. Okay, so it's going to be really difficult to achieve congruence between these two platforms for Pompe disease, even if we use conversion of the micromoles per hour per liter to percent of daily mean or percent of weekly mean. We're still going to get non-congruence. Okay. I just want to say one more thing about this Pompe maltase glucoamylase problem, non-congruence between digital microfluidics, fluorescence, and mass spec. With respect to the CDC QC standards, the dried blood spots, if you were to plot micromole per hour per liter, here's your base, here's your low, medium, and high. You'd get something close to the origin for mass spec. But the digital this is mass spec. The digital microfluidics curve would have a higher slope. I told you the buffer is more optimized, but it would also go pretty close through the origin here. Slope's higher. You don't see this interference from maltase glucoamylase, and you have to be very careful here. That's because, remember, the CDC depletes the leukocytes and they heat treat the blood. So presumably most of the GAA and the maltase glucoamylase in the QC standards are killed off by these treatments. And so there's essentially, in the base pool, the activity of both enzymes is close to 0, and you don't see the interference from maltose glucoamylase with digital microfluidics or mass spec. But it's not the same story when you take real dried blood spots from infantile onset Pompe disease patients, where you have not depleted the leukocytes and have not killed off the enzyme with heat treatment. We expect the amount of GAA activity to be very close to 0 in these infantile samples. Most of these patients are CRIM negative. They don't have any protein, GAA protein. And yet digital microfluidics gives about 20% of mean activity for these samples, whereas mass spec's more like 5%. So this is due to the MGA contribution to digital microfluidics. And you should not get fooled by the fact that both give close to 0 activity on the base pool, both techniques. Okay, you got to be very careful here, right? So let's talk about now MPS1. So it's interesting. Here we expect pretty good congruence between digital microfluidics and fluorescence, and we see that. So here's the iduronidase substrate. Remember, IDUA is the enzyme. And this is iduronic acid, has the carboxyl group down, has some hydroxyl groups. Never mind the exact structure. Here's the 4-MU fluorescence. But it turns out the way we make this is by isomerizing the isomer with the carboxyl group up. We convert it to the carboxyl group down. And so, usually preparations of the carboxyl group down, substrate are contaminated with small amounts of carboxyl group up. And that's a problem because this is not idiuronic acid, this is glucuronic acid. And in the blood spot is large amounts of beta glucuronidase, also called GUS-B, that would readily hydrolyze this beta. So this is alpha, this is beta, and produce the 4-MU. So even if IDUA is 0 in a severe MPS 1 patient, you might get some 4-MU fluorescence if there's a little bit of the beta isomer. And that's also true for mass spec. And so the way we deal with this is we add a inhibitor of GUS-B. And never mind the inhibitor, it's glucuronic acid, I think 1,4-lactone, I think it's called. And in both buffers, I feel that the concentration of the beta glucuronidase inhibitor is more than sufficient to totally take out all of the beta glucuronidase activity. And so we really don't have any off-target problem here. If you give me a sample that has 0 iduronidase, digital microfluidics is going to read very close to 0 activity, and mass spec the same thing. And so we expect that if we convert the digital microfluidics fluorescence data to percent of mean, and the same for mass spec, that we expect good comparison. And in fact, this is what we see. In fact, Missouri uses 7.2% for their cutoff for IDUA, expressed as percent of mean. And New York uses, I think, 6.5%. So they've settled on very, very similar cutoffs. This is not the case for Pompe disease. Remember, for Pompe disease, Missouri uses about 25%. And New York uses about 15%. But for MPS 1, we see a lot more congruence because there's essentially no contribution from off-target enzymes. All of the activity is due to IDUA. And if we convert to percent of mean activity, we can deal with this alpha-beta problem that I mentioned to you earlier about different slopes, different activities on different substrates and different buffers. It sort of cancels out if we convert to percent of mean. So it's going to be a lot easier to achieve congruence between these two assay platforms for MPS 1, but difficult for Pompe disease. Okay. So in the last segment of this tutorial, I'm going to talk about how QNMR is used. This is kind of an appendix. Listen, if you're interested, it's not critical. But let's say a little bit about quantitative NMR. So let's go back to cycosine. Here's the chemical structure of cycosine. It has a galactose, has this hydroxyl group here. Up, down, up. So this is the galactose part attached to the sphingosine part. Here's the amino group, another hydroxyl group. Here's a double bond. Then it has 12 methylenes and a methyl group. So that's cycosine. Cycosine. Now, I didn't draw in all the hydrogens. There's a couple of hydrogens here. There's one here. There's one here. There's one here. Here. Doesn't matter. Here. 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 There's two here. And it turns out that each of these hydrogens, if you put them in a magnetic field, they absorb radio electromagnetic radiation. Okay. So it turns out that the different hydrogens in the different structural elements of cycosine absorb slightly different frequencies of radiation. And so if we plot the absorbance of RF versus the frequency, and this is usually expressed in a scale called chemical shift. I'll just call it delta. The details aren't that important. So these protons here, these hydrogens that are attached to a double bond, they tend to give a peak. There's two of them here. Apparently there's two of them. Well, apparently the structure is, there's exactly two of them. And this is around 6 parts per million. The methyl group, here it is, around 0.9 parts per million, etc., etc. And, NMR spectroscopists have studied this for more than 50 years, and they know exactly where these hydrogen atoms in the molecule, according to their structure, are found in the NMR spectrum. Okay. Now, the beauty of NMR, for our purposes, is that the area under this peak is proportional, let's call it alpha, to the number of protons, number of hydrogen atoms that are in that peak. Okay? And this area is also proportional number of hydrogens in that peak, and alpha is the same constant in both cases. So what does this mean? That means, well, here we have 3 hydrogens in the methyl group, and we have 2 protons, hydrogens on the double bond. So we expect this area to be divided by this area to be 3:2. And in fact, that's what we see. 3:2 as a ratio of the areas, as predicted by the number of hydrogens in the structure of cyclosine. Guaranteed. Except for one problem. Maybe underneath this peak are hydrogen atoms from some impurity that we don't know about is in the sample. If that were true, then this would be a little bit higher than this ratio. 3:2 would be, this number would be a little bigger, and the ratio would be a little bit less than 1.5. But the fact that the ratio of this area to this area is 1.5 suggests that we don't have an impurity buried in this peak. It also suggests that we don't have an impurity over here. Well, you could be a cynic and say we have some impurity area under here and the same amount of impurity area under here, and so the ratio is still 1.5 to 1, 3:2. But we can play this game for all the different hydrogen atoms in cyclosine. They all give rise to different peaks. And for any pairwise comparison, we know from the structure, these two, there's 2 hydrogens here, there's 1 here, 2-to-1 ratio. So we expect all of these ratios to be true. And if that is in fact the case, we can say with high confidence that these peaks are not contaminated by hydrogens of impurities. Now, you could be a cynic and say there could be hydrogens contaminating all of these peaks in just the right way so that all of the ratios come out exactly as predicted by the cyclosine structure. But that, life's too short to be such a cynic. Okay, so we kind of rule that out. It's very unlikely. All right. So the beauty of NMR is that the area of these hydrogen atom peaks are proportional to the number of hydrogens in the molecule. So in a sense, these count the hydrogens in the molecule. Now, this is true even if the cyclosine is not pure by weight. Maybe there's some water in the cyclosine. Water has some hydrogens. It gives rise to a signal here at about 4.5 delta. But that's okay, because the area of this water peak has nothing to do with the area of the peak due to these hydrogens on the double bond. Okay? So impurities, if they show up as additional peaks in our spectrum, just ignore them. Unless, of course, they lie underneath the peaks of the cyclosine, but we already ruled that out. All right. So this area relationship is true regardless of whether the cyclosine is pure by weight. It just depends on the chemical structure of cyclosine, which has nothing to do with its purity by weight. All right, so now, the area under this curve is proportional to the number of hydrogens, but it is not equal to the number of hydrogens, right? There's a proportionality. So to convert this area into hydrogen count, we need an internal standard. All right, so what do we do for the internal standard? So we use a molecule like dimethyl formamide. Here it is, the structure. And the nice thing about QNMR internal standards is that you can buy NIST certified internal standards for NMR, because NMR is so powerful for determining the amount of moles of substance in the sample, in the vial. Companies have produced certified NMR internal standards. Now, this argument is somewhat circular. If we're going to use QNMR to certify something, how do we certify this? Well, we have to assume that this is pure by weight. But fortunately, we can do this with high confidence because dimethylformamide, it's a simple molecule. It can be distilled many times in glass. It's easy to get water free of heavy metals. We can get it to the point that we are sure with high confidence that's pure by weight. Maybe some internal standards are purified by recrystallization, so we can get them with high confidence pure by weight. So then we can weigh out the cyclosine on a balance. So we had 1 milligram, and it's pure by weight. So with the molecular weight, we know how many moles of DMF, dimethylformamide, we're adding to the NMR sample. So here's the peak due to the hydrogens of dimethylformamide. There's this guy over here, and these methyls tend to be two separate peaks here at around 2. And we see the peaks due to the NMR, due to the internal standard. And so we know that this peak, the area, is proportional to the number of hydrogens in the DMF. But we know how many hydrogens are in the sample because we know it's pure by weight. We know the weight that we added. We know the molecular weight of DMF. So how does this work? So this is due to the 1 hydrogen atom in DMF. Here it is. And this peak here is due to the 2 hydrogen atoms on the double bond of cyclosine. So if the moles of cyclosine in the NMR sample tube equals the moles of DMF in the same tube, if the moles of if the moles are the same, we expect the area here to be twice the area here, because this is 2 hydrogens, this is 1 hydrogen. Okay, so if we add 1 micromole of cyclosine to the sample, and this area is twice that area, we know we have 1 micromole of cyclosine in the sample. Okay, and we can play this game, and we can therefore determine the absolute moles of cyclosine in the sample, regardless of the fact that it might not be pure by weight. And that's exactly what we do with QNMR. And you can see now why this is a very nice technique for determining the absolute moles of substance in a vial, because it's true regardless of whether the vial contains impurities or not. Even if the compound is not pure by weight, the game still works. As long as our internal standard is pure by weight, then we know exactly how many moles we added to the sample as an internal standard by weighing it and using the molecular weight. Okay? And we have ways to purify simple compounds like dimethylformamide, get them pure by weight with high confidence. NIST certified. Okay, so now you know how PerkinElmer determines the absolute moles of internal standard in their vials for their LSD reagents. They do it by QNMR. This is how I made mixtures of product to internal standard of known mole ratio by doing QNMR. It's really the best way to know the absolute moles of substance in a vial.